Hello everyone. Today we are going to learn about subject called operating system, and the subject code is SCIT 2230. In this subject, we are going to focus in this session that is regarding memory management unit. What is memory management? What the topics we are going to learn regarding memory management of operating system, that is listed down over here. When memory management is one of the roles, or let's say responsibility of operating system. As a responsibility of operating system will perform different kind of functionalities to maintain this particular memory management responsibility. So in this session we are going to talk about what is main memory, what are the basic knowledge you require to understand main memory, then what is swapping process. Then there are different types of memory management techniques, that is contiguous allocation techniques and non-contiguous allocation technique. We are going to learn in detail about what is contiguous memory allocation techniques and what is non-contiguous memory allocation techniques. What are the different techniques can be categorized as a contiguous as well as a non-contiguous memory management technique. After that, we are going to focus on a page replacement algorithms. So this is one of the functionality which operating system will perform on the behalf of memory management responsibility. So in this page replacement algorithm, we will cover optimal page replacement algorithm, FIFO page replacement algorithm, least recently used, not recently used, second chance page replacement algorithm. And after concluding all of this, we will see one of the effects called crashing and what is the reason of happening this effect that we are going to cover. So these are the topics which we are going to cover in this module. So we will start with obviously memory management. That first we need to understand what is memory management. After getting basic clarity about memory management, we will be focusing more on what kind of functionality operating system will provide on behalf of memory management responsibility. So what is memory management? So main memory, we are mainly there are two types of memory available in computer system. That first one is primary memory and second one is a secondary memory. So what is primary memory? Primary memory, the other name of primary memory is main memory, or let's say RAM. So main memory refers to a physical memory, that is the internal memory to the computer. That means the word main is used to distinguish it from the external mass storage devices such as a disk drive. So main memory, that is that can be considered as a RAM, or let's say primary memory of the computer system. So main memory is also known as a RAM, that is nothing but random access memory. So main memory is mainly used to store process data, or let's say process, and using that particular memory, your process will execute in computer system and it will complete its execution with the use of CPU as well as operating system and memory. So the computer is able to change only data that is in main memory. Your CPU, that is CPU is not allowed to access any data or to change any data of secondary storage. CPU is only allowed to use main memory. So whatever process you want to run, so whatever program you want to execute in computer system, that should be in a main memory, then and then your CPU will able to change it, or your CPU will able to access it. So therefore, every program, whatever program we want to execute or whatever file we want to access, that must be copied from storage device to the main memory. So that particular task of managing secondary memory data as well as main memory data, that comes into the memory management responsibility of operating system. So memory management is the functionality of an operating system which handles or manages primary memory and moves process back and forth between main memory and disk during the execution. So memory management is nothing but one of the functionality which is going to be provided by operating system to manage your processes such that each and every process will get a fair chance to execute itself and complete its execution. So memory management keeps track of each and every memory location, regardless of either it is allocated or to some process or it is free. So one of the tasks of the memory management responsibilities, you have to keep track of main memory data. So how many locations are currently free, how many locations are currently occupied by the processes that are going to be maintained by using memory management functionality. So it checks how much memory is to be allocated to process. It decides which process will get memory at what time, and it tracks whenever some memory gets freed or unallocated when the process completes its execution, and it will update the status accordingly. So these are the different tasks which can be categorized in terms of memory management functionality. So there are different types of memory. So first we will get a clarity about what are the different memories available in computer system and how it differs from each other. So this is one of the hierarchical structure or hierarchical arrangement of storage in current computer architecture, and this is called memory hierarchy. So as you can see, at the topmost level, we have write down memory called register. After that, L1 cache, after that, L2 cache, after that, main memory, then local secondary storage, and after that, remote secondary storage. So if we go according to this order, from bottom to top, the memory access time becomes faster. So if we compare register and main memory, so register has a faster access of data compared to main memory. Same way, if we talk about in terms of cost, then register memories are more expensive compared to L1 cache, L2 cache, main memory, local secondary storage, or remote secondary storage. Same way, if we talk about capacity, from bottom to top, as we go above, the capacity becomes less. So we have a highest capacity in a remote secondary storage. Remote secondary storage are cheaper compared to above memories, and they are slower compared to others. So based on this categories, we have classified this, that register memory is faster to all listed out memory. It is more expensive compared to all other memories, and it has a less capacity compared to all other memories. Likewise, if we talk about remote secondary storage device, then remote secondary storage have a highest capacity, less expensive, or let's say cheaper compared to other, and it is slower in data access tasks. So these are the memory hierarchy. These are the different memories available in computer system. Our focus right now, our focus is currently in this main memory. We are going to focus on main memory, how the operating system will manage main memory for execution of process, that we are going to discuss in this particular module. So the next is logical and physical address. To go in deep regarding main memory, first we must have a clear idea about what are the different addresses computer system will works with. So there are two types of addresses available in computer system. First one is called logical address, and the second one is called physical address. So logical address, or let's say another name of logical address, is virtual address. So it can be viewed by user. The logical address can be viewed by user. The user can't view the physical address directly. The only address which is directly accessible by user, that is logical address, because logical address is going to be generated by CPU. Whenever any process comes into the execution, CPU will generate logical address. Operating system, or let's say to be very precise, you will compute the mapping between logical address and physical address, and it will find out the actual location of that particular data in the memory. So the address which is directly viewed by user, that is called logical address. That is not actual address where your data is stored in the memory. The actual address, that is called physical address, and that is not directly viewed by the user. So the fundamental difference between logical address and physical address is that logical address is generated by CPU during the program execution, and the physical address refers to the location in memory unit. So the physical address is the actual address where your data is stored in the memory unit. So physical address is going to be computed by which unit? MMU. The full form of MMU is Memory Management Unit. Memory Management Unit is responsible for mapping between logical address and physical address. Now the next is the structure of MMU, that is Memory Management Unit. So hardware device that maps virtual to physical address. So this is the basic structure of MMU. MMU will comes between CPU and the main memory. Whatever address is going to be generated by CPU, that is called logical address. Let's say CPU has generated logical address 3, 4, and 6. MMU will have something base address from the respective registers or respective data, and that base address is going to be added into the offset which is generated by CPU, and the physical address is going to be identified by MMU, and that physical address is the actual location of the data in the memory. So in MMU scheme, the value in the relocation register, this particular relocation register is going to be generated by the operating system, that what actually base address you have to consider for finding out the actual address of the data. So the mapping between virtual to physical address is the whole and sole task of MMU. MMU is nothing but Memory Management Unit. Now the next is memory management requirements. Basic requirements which memory management functionality must satisfy, that is this two, relocation and the protection. What is the relocation? So programmer cannot know where the program will be placed in the memory when it is executed. Whenever we run, let's say if we talk about any simple C program, whenever you compile it and after that you will execute it, you are not concerned about where it stored into the computer system. You are only concerned about what will be the output of my program. So same way, programmer cannot know where the program will be placed in memory when it is executed. So process may relocate it in main memory due to swapping. Let's say we have executed our program, but at that time any higher priority task comes into the operating system. So operating system will give priority to that particular higher priority process. So there might be possibility that our program got swapped out and the higher priority process goes into the execution. So it might be possible that first whatever address is allocated to our process, that can be changed due to swapping. So reallocation must be possible in memory management requirement. Then and then we will satisfy multi-programming in computer system. And the second functionality or second requirement is protection. The main aim of it is to prevent a process from accessing memory that has not been allocated to it. Process is allowed to use the memory address which is already allocated to it, but beyond that particular limit, the process are not allowed to access the memory. So this protection must be there. Then and then the data consistency can be stored or maintained. Next is base and limit registers. So how the memory protection is going to be implemented in operating system. So using this base and limit registers, we are going to maintain protection requirement of our memory management. So an address space is set of addresses that a process can use to address the memory. Whatever process required, whatever size of memory process is required, that is going to be allocated in operating system, or let's say in computer system. So let's say this is one of my process which is currently stored in the main memory. So the starting address of that particular allocation is called base address. Base address is nothing but what is the starting address of my process, and the limit register is nothing but actual size of the memory which is occupied by that particular process. So let's say the base plus limit, that is going to be given me the ending address, last address of the process which process is allowed to use. Beyond this particular limit, this particular range is only accessible by this particular process. If this process wants to execute any of the data beyond that particular limit, that is not allowed, and that is called memory protection. So an address space is a range of valid addresses in memory that are available for program or processes. So there are two registers to maintain this particular protection, that is called base and limit. So base register is nothing but it will store the start address of the program in the physical memory, and limit register is nothing but length of the program, or let's say size of the process, how many data or how much size it has occupied in our memory. So for every memory access, base is added to the address result and compared to the limit. If it is goes into the valid range, then we are going to allow the access of that particular memory. If it is goes beyond this particular limit, then we are not going to allow process to access that particular data. So only OS can modify base and limit register. No one is allowed to change the base and limit register except operating system. Now the next one is hardware address protection using base and limit register, what we are going to discuss. Same they have explained over here, that how protection of memory space is accomplished by having CPU hardware compare every address generated in user mode with the register. Any attempt by user program running in a user mode to access the memory space of operating system or any other user program result in a trap. It will generate error, or let's say trap instruction, that your CPU or your process wants to access those data which is not assigned to it. So we are not going to allow to access that particular data. So the scheme prevents a user program from modifying the code or data structure of operating system or another user program. So what is dynamic reallocation? So steps of dynamic reallocation is hardware adds relocation register to virtual address to get the physical address. Whatever address is going to be generated by CPU, that is called logical address. That logical address is going to be converted into physical address by finding out the base register value. That is nothing but starting address of that particular process, and whatever offset they have generated, that is going to be added, and one physical address is going to be find out. After finding out the physical address, we are going to check whether it goes into the given limit. If yes, then we are going to allow to access that memory. If it is beyond the limit register, then we are going to generate error, or let's say trap instruction to address, to tell the CPU or to tell the operating system that ignore this particular request because they are want to access those data which are not accessible by those. So address error is going to be generated to inform CPU that kindly generate a proper logical address. So after that, the next process which we are going to learn, that is called swapping. So what is swapping? So swapping is a mechanism in which a process can be swapped temporarily out of main memory to the secondary memory and make that memory available to other process. At some time, a later time, the system swaps back those process from the secondary storage to main memory. So swapping is also known as a technique for memory compaction. So what actually happens in operating system is, whenever we want to execute any process in operating system, that process must be present in main memory. Then CPU is allowed to access those process. So what happens when the process wants to execute, the process must be in a main memory. Let's say due to any one of the task, higher priority process comes into the operating system. So operating system will obviously give the priority to the high priority task. So what happens, for some temporary amount of time, whatever process is currently loaded into main memory, that particular process swaps out from the main memory to secondary memory to utilize the main memory sufficiently. So whatever lower priority process are present in main memory, that is going to be swapped out from main memory to secondary memory, and instead of that low priority process, higher priority process takes place in main memory, and after that getting access of main memory, it will goes into the execution. So this kind of process or this kind of logic is very much important for the multi-programming execution in the operating system. So swapping is one of the mechanism using which you can move some of the process from main memory to secondary memory, as well as you can move some of the process from secondary memory to main memory. So this actual there are two subtasks in the swapping. One is called swap out and second one is called swap in. So what is swap out? Whenever you move process from main memory to secondary memory, that particular task is called swap out. And whenever you move one memory from the secondary memory, that is called swapped in, from secondary storage to main memory. So this is the semantic view of swapping. So this is my actual main memory. Some of the portion is going to be used by operating system itself, and the other partition of the main memory is going to be used by processes. So whenever you move one process from main memory to secondary memory, that particular process is called swap out. And whenever you move one process from secondary storage to main memory, that is called swap in. So this actual whole process of swap out and swap in is nothing but swapping. So swapping is important to maintain the multi-programming, or let's say multitasking functionality of operating system. After that, we are going to discuss memory management techniques. So how we are going to handle memory for process allocation, that we are going to discuss now. So your memory management techniques are divided into two categories: contiguous allocation and non-contiguous allocation. Your contiguous allocation process techniques are furtherly divided into two parts, that is fixed partition scheme and variable partition schemes. Same way, non-contiguous memory allocation is further classified in a paging, multi-level paging, inverted paging, segmentations, and segmented paging techniques. So fixed partition scheme and variable partition scheme is a part of contiguous memory allocation, and paging, multi-level paging, inverted paging, segmentation, and segmented paging, that are category of non-contiguous allocation. So before discussing in detail each and every techniques in detail, first we need to understand what is contiguous allocation and what is non-contiguous allocation. So till now, what we have a clear idea about, that whenever process wants to execute, that process must be present in main memory. Then and then your processor is allowed to access that particular process, and it will complete the execution of that process. So obviously, whatever or whichever process wants to execute, that process must have a allocation in main memory. So that allocation can be of two categories. Either that allocation can be contiguous or that allocation can be non-contiguous. So what is the difference between contiguous and non-contiguous? Let's say one process of size 100 MB comes into the operating system, and that process wants to execute. So operating system will either use contiguous allocation technique or it will use non-contiguous allocation technique. Let's say your operating system is currently designed on a contiguous memory allocation. So what happens? Whenever process comes into the operating system will check how much memory it required to store this particular process. So the size of process is 100 MB. So 100 MB is required for that particular process to be stored in a main memory. So operating system will find out whether I have a contiguous free 100 MBs in main memory. What operating system will check? Whether I have a contiguous address space free of size 100 MB, then and then I'll be able to allocate that particular process into the main memory if your operating system is designed on a contiguous allocation. Let's suppose your operating system is working on a non-contiguous allocation, then what it will check? It is not necessary that I'll require contiguous 100 MB space free. Then and then I'll be able to allocate that particular process into the main memory. If I have a segregate memory available at different location, but the summation of that free memory is 100 MB, then allocation of that process is possible in non-contiguous allocation. So there are two mechanisms. either your process is going to be allocated in memory in a contiguous manner or in a non-contiguous manner. So first we will focus on a contiguous memory techniques, the different types of contiguous memory schemes, and after discussing it, we will move towards to the non-contiguous allocation. So there are two types of allocation as we have discussed. So memory allocation is process by which computer programs and services are assigned with a physical or virtual memory space. So memory allocation is the process of reserving a partial or complete portion of computer memory. So there are two types of memory allocation, contiguous memory allocation and non-contiguous memory allocation. So what is contiguous memory allocation? So in contiguous memory allocation, assign a process consecutive memory blocks. That is, memory blocks having consecutive address, then and then we are able to allocate that particular process in memory. So when a process needs to execute, memory is requested by the process. The size of process is compared with the amount of contiguous memory available in the execute, and then after analyzing it, the operating system will allocate memory to the process. So contiguous memory allocation. So if sufficient contiguous memory is found, then the process is going to be allocated and it will start its execution. Otherwise, it is going to be added in a waiting queue until and unless that sufficient pre-contiguous memory is not available. So main memory usually has a two partition, low memory and high memory. So in low memory, operating system resides in this memory. Obviously, to run operating system also use or also occupy some of the main memory part. So that part is called low memory and remaining part is called high memory, where your user process are going to be allocated. So partitioning in contiguous memory allocation, there are three techniques: single process monitors, multi-programming with fixed partition, and multi-programming with variable partition. So multi-programming, that means we have a more than one process available into the main memory, that is called multi-programming. Single process monitor, that means at a time only single process is allowed to be in an operating system, that is called single process monitor. So these three are the partitioning techniques, or these three are the allocation techniques in the contiguous memory allocation. So if we talk about single process monitor, that means your main memory is going to be divided into two parts. One is going to be occupied by operating system and the second is going to be used by the user process. So single process monitor, that means here main memory is of, let's say, 500 MB. So space is reserved for operating system. In main memory, let's say 500 MB is already occupied by operating system and the second part is going to be used by the user process. So in single process monitor, only one process can load into memory at a time. Only single process is allowed to be loaded into the main memory. So when one process will complete the execution, next process is going to be loaded into the memory. So single process monitor does not support multi-programming. It only supports uni-programming. Uni-programming, that means only single process is going to be available, or only single process is going to be present at a time in main memory for single process monitor. After that, we are going to learn about multi-programming. First, we are going to discuss with fixed partition, and after that, we are going to discuss with the dynamic, or let's say variable partition. So here your memory is going to be divided into the fixed size partition. Let's say this is my main memory. That particular main memory is going to be used. Some of the portion is going to be used by operating system. And after that, for the user process, I have created four partition. One partition, second partition, third partition, and fourth partition. As you can see in the diagram itself, that partition size can be unequal. It is not necessary that all partition must be of equal size. It can be of different size. That is totally allowed. So generally unequal partitions are going to be used for better utilization. Obviously, all the process must have a different sizes requirement. So if we divide our process into equal size partition, then it might be possible that our main memory is not going to be utilized properly. So unequal partition is going to be generally used for the better utilization. So if bigger process comes into the operating system, we have a partition for same also. After that, each partition can accommodate exactly one process. That means in partition 1, I am only allowed to allocate one process. That's it. The remaining part is not going to be used by any other process. So per partition, only single process is allowed. So the partition boundaries are, the next one is the partition boundaries are not movable. You are not allowed to change the size of partition after creating it. So the size of partition is created at the starting of itself. After that, you are not allowed to change the size of partition. This is the fixed size. Based on your requirement, you can allocate your process in any of the partition, but per partition, only single process is going to be allocated. So whenever any program needs to be loaded in memory, a free partition which is big enough to hold that program is going to be found, because which techniques we are currently learning? Contiguous allocation. So consecutive address space is going to be allocated to that particular process. So that particular partition is going to be allocated to program or process which is big enough to hold that particular process. So if there is no free partition available of required size, then the process needs to wait. Such process will be put in queue, or any process with lower priority can be swept out to make a room for a higher priority process. Either two possibilities are there. Either that particular process is going to be in a waiting queue, or if the process priority is higher, then we are going to select some of the process to perform swap out operation, and based instead of that particular process, we are going to allocate this particular partition to the higher priority process. So let's say we are going to explain this using one of the example, but before that, whatever process are going to be put it into queue, there are two techniques to maintain it. Either you can use multiple queues. That means per partition, you are allowed to use separate queues. I have a one separate queue for partition 1, another separate queue for partition 2, partition 3, as well as partition 4. Or you can manage a single queue for all the partition. That is totally up to you, which technique you want to use to keep track how many processes are currently in a waiting queue. So advantages of contiguous allocation, or let's say, as if we say very precisely, fixed partition, multiple programming with fixed partition. Advantages are it is simple to implement. Disadvantages are the problem of internal fragmentation that we are going to discuss in after two or few more slides. And obviously the memory is not going to be used efficiently, because we are going to create a partition at the starting point itself, and we are not sure whether that partition is going to be utilized properly or not. So it is not efficient to use for better memory utilization. So let's say next technique is multi-programming with dynamic partition. So what is the basic difference between multi-programming with fixed partition, multi-programming with dynamic partition? That clearly see from the name itself. One is of fixed partition and second one is of dynamic partition. That means whatever difficulties we were facing in a fixed partition, that is going to be removed in a dynamic partition. So to avoid the difficulty of fixed partition, now we are going to create a partitions dynamically. So whichever size of process comes into the operating system, based on that partition are going to be created. So in dynamic partition, no partition is fixed into memory, but the partition are created only when the process is loaded into the memory. So initially, the entire available memory is treated as a single free partition. The partition size is exactly size of the process. So whatever size of process comes into the memory, based on that partition are going to be created into the memory. So let's say if a process size is of 125 MB comes into the memory, so one partition is going to be created of 125 MB, and the remaining partition is going to be created for other process utilization. So let's say, let's explain this particular multi-programming with a dynamic partition using one of the example. So let's say there are 6 processes which are going to be comes into the operating system, that is P1, P2, P3, P4, P5 and P6. And the sizes of each and every process is already mentioned over here. Now what we are going to see that how the partitions are going to be created in a dynamic partitioning technique. So the 0 to 500 MB is going to be occupied by operating system itself, and the remaining memory is going to be used by the user process. So currently there is no partition. You can see the user process is a single partition available of size 500 MB. Now whichever process comes, based on that the partition starts to creating. So initially the partition size is of 500 MB. Now the first process comes into the operating system of 110 MB. So one partition is going to be created by P1 process of how much size? 110 MB. And the remaining partition is going to be created for other process to utilize it. So as you can see over here, when the process will load, then the partition is going to be created as per the size of process. So initially the whole partition was free. After that, P1 loaded into the memory, one partition is created of 500 to 610 address space, that is nothing but the size of 110 MB. And 610 to 1000, that address space is currently free now. Now let's say next process comes into the picture. So according to that size of that particular process, next partition is going to be created, that is 610 to 690, and the remaining memory is going to be free. Same way, P3 is going to be loaded. Likewise, P4 is going to be loaded and P5 is going to be loaded. After that, the size of P6 is not, for P6, we don't have a sufficient memory available into the main memory. So P6 is not going to be allocated. So in dynamic partition, the partition is not decided at the starting itself. It is going to be created according to the process size. So let's say in our example, the size of process P1 is 110 MB. So partition of 110 MB is going to be created, and the remaining memory is going to be created as second partition, which is currently free. Likewise, whatever process comes into the picture, based on that partition are going to be created in dynamic partitions. Let's say, and the last process P6 comes into the picture. The size of P6 is larger compared to the free memory which we have available. So we are not going to be we are not allowed to use that particular free memory for P6 because we want contiguous allocation for P6. So in dynamic partition, there will be no internal fragmentation, but still the external fragmentation is present in dynamic partitioning technique. What is internal fragmentation? What is external fragmentation? That I am going to explain using one example later on in this particular section itself. But before that, let's understand this particular diagram. So this is nothing but multi-programming with dynamic partition. So initially, I have only two partitions available. That is, one is partition is going to be occupied by operating system, and the remaining is going to be used by user process. Now, let's say first process comes into the picture of name A. Whatever size of memory it requires, based on that partition is going to be created, and the remaining partition is going to be free. After that, B comes into the picture. After that, C comes into the picture. Same way, this partition are going to be created. After that, let's say A completes its execution, so it will free this particular memory. And if D comes into the picture, based on the size of D, we are going to allocate memory into the main memory. So operating system will check what? Whether I have a sufficient contiguous memory available for appropriate process or not. If yes, then it is going to be allocated. If no, then it will going to be, that process is going to be weighted into the waiting queue. After that, the advantages of dynamic partitioning is no extra internal fragmentation are there, and your memory is going to be utilized properly compared to fixed partition. And the disadvantages is still we are struggling from external fragmentation, and it is not easy to implement dynamic partitions because we are not know what size of process are going to be comes into the picture, how many partitions are going to be created of what sizes. So it is not easy to implement. So now we are going to discuss about fragmentation. So what is fragmentation? So as process are going to be loaded and removed from the memory, the free memory space is broken into the little pieces. Let's say first process comes into the picture. After some amount of time, that process is going to be complete its execution and it will leave the memory. So by completing this kind of task, your main memory space is going to be divided into different small partitions. And it happens after some time that process cannot be allocated to memory blocks considering their small size. And those memory blocks are going to be remain unused. And this problem is called fragmentation. Whatever process comes into the operating system, it will use main memory and it will leave that particular main memory after completion of its execution. So whatever free different small sizes pieces are available in main memory which are not going to be utilized by process properly, that particular fragments or that particular small partitions are called, that particular problem is called fragmentation. So there are two category of fragmentation. One is internal fragmentation and the second one is external fragmentation. So your fixed partitioning in contiguous allocation, there are two techniques which we have learned, that is fixed partition and dynamic partition. So your fixed partition techniques suffer from both internal fragmentation as well as external fragmentation. And your dynamic partitioning technique suffers from external fragmentation. It successfully overcome the internal fragmentation. So what is internal fragmentation? So it arises when the memory allocated to program is not fully utilized by it. This form of fragmentation occur whenever the size of program loaded is smaller than the size of partition. So in fixed partition, we are creating partition at the starting point itself. So let's say one partition is created of 100 MB and one process comes into the picture of size 90 MB. So as I have told you earlier that you are not allowed to allocate single partition to more than one process. Only one process is allowed to load it into that particular partition. So 90 MB process is going to be loaded into 100 MB partition. So remaining 10 MB is going to be unutilized until that process is present in operating system. And that particular unutilization of that particular 10 MB size of fragment is called internal fragmentation. So difference between total space of partition minus space occupied by the process is called internal fragmentation. So the size of partition was 100 MB and the size of process was 90 MB. So 100 minus 90 is equal to 10 MB. That 10 MB is called internal fragmentation. So let's understand this particular concept by one of the examples. So here there are four processes already loaded into the memory, that is P1, P2, P3 and P4, and the size of each and every partition is going to be mentioned over here. That first partition is going to be created for 110 MB, then 80 MB, then 40 MB. Sorry, the size of P1 process is 110 MB, P2 process is 80 MB, P3 process is 40 MB, and P4 process is 120 MB. In fixed partition technique, the partition size is decided at the starting itself. So first partition was created of 150 MB because the starting address of that particular partition is 500 and the ending address is 650. So the size of this particular partition is 150. Same with size of this partition is 100, size of this particular partition is 50, and the size of this particular partition is 200 MB. So if we talk about very first partition, so size of this partition is 150 MB, but the P1 process size is of 110 MB. So 150 minus 110, that means 40 MB space is wasted. That is not going to be utilized by any other process, and this is called internal fragmentation. And this type of problem is also occurred in other partitions also. If we talk about this also, the size of this particular partition is 100 MB and the process size is of 80 MB. So internal fragmentation is created of 20 MB. Same way, all remaining two partitions also suffers from internal fragmentation because the size of this process partition is 50 and the process size is 40. So 10 MB is going to be unutilized. Same way, size of this particular partition is 200 and the size of process is 120. So 80 MB is internal fragmentation, or 80 MB, that particular memory is going to be unutilized for that particular partition. So this is called internal fragmentation and it is only present in a fixed partitioning technique of contiguous memory allocation. Now let's talk about external fragmentation. So what is external fragmentation? So total memory space is enough to satisfy a request or to reside a process in it, but that particular space is present in a non-contiguous manner. That is called external fragmentation. Let's understand this particular concept using this example. Let's say this is the current allocation of main memory. We have allocated P1 to P8 process into the main memory, and based on that over here, the size of process as well as partition is mentioned over here. Now let's say if P1 complete its execution. Obviously, if P1 completes its execution, it will deallocate the space which is already allocated to P1. So P1 will complete its execution and leaves this particular partition. So the size of this partition is 30 MB. That is going to be free. After that, let's say P3 also completes its execution and it will deallocates the memory. So the size of this particular P3 partition is of 50, 100 to 150. That means 50 MB is of size of P3. So P1 has completed its execution. P3 is also complete its execution. So that means these two partitions are currently free in main memory. Now the new process comes into the picture of size, let's say 60. So if we scan our main memory, operating system scans the main memory, it will find out that yes, I have one partition free, but that partition size is 30 MB and the process requires 60 MB. That means I am not going to allocate that particular process in this partition because it is not feasible enough. That particular partition is not big enough to hold this particular P9 process. After that, it will scan and it will find out this particular partition is also free, but the size of partition is 50 MB and the process requires 60 MB. So this single partition is also not sufficient enough to hold that particular process. But if we talk about the total memory which is currently free in main memory, that is nothing but 30 plus 50. That means I have a free memory of 80 KB available in my main memory. Still, I am not able to allocate P9 because this particular 80K is not available in contiguous manner. The reason of that particular non-contiguation leads to the non-allocation of P9. So this kind of memory unutilization is called external fragmentation. That means I have the enough memory free available in main memory. Still, I am not able to allocate process in that main memory because the memory which is currently free, that is not in a contiguous manner. Due to that reason, I'm not going to allocate P9 in the main memory, and this kind of memory unutilization is called external fragmentation. So your multi-programming with dynamic partitions suffers from external fragmentation. Although it is possible to allocate P9 in main memory, still we are not able to allocate it because it is non-contiguous. So this is the one of the drawback of contiguous memory allocation technique. So to overcome this particular disadvantage, that is nothing but external fragmentation, one technique is available that is called memory compaction. So memory compaction technique can be used to create more free memory out of fragmented memory. Due to that process comes into the operating system, completes its execution and leave the memory, this kind of fragmented memory is going to be created, which is not going to be utilized properly by contiguous memory allocation techniques. So what memory compaction technique will do? Memory compaction technique will do this particular task, that it will combine occupied partitions at particular one direction, and it will combine the free partition into the single one partition of this particular main memory, and that is called memory compaction. That means we are going to resize all the used partition at one direction, and we are going to combine all the free partition into the single partition. So all these four free partition is going to be merged out and going to be create one single free partition, and all the occupied, or let's say used partition, are going to be moved towards to the one direction. So this technique is called memory compaction technique, that can be used to solve external fragmentation in dynamic allocation technique or multi-programming dynamic allocation techniques. So that was all about what is contiguous memory allocation, what are the different techniques available into the contiguous memory allocation, what are the advantages of those techniques, what are the disadvantages of those techniques, what is fragmentation, types of fragmentation, what is internal fragmentation, what is external fragmentation, how to overcome external fragmentation. So after that, we are going to discuss about different allocation algorithms, that how we are going to allocate process into the main memory in contiguous allocation. So there are many strategies to allocate process into the free partitions, and that particular techniques are this four: first fit, best fit, worst fit, and next fit. According to the logic fit by the operating system, either your operating system will allocate process according to first fit, or it will use according to the best fit, worst fit, and next fit. So let's understand how it actually works. So how your operating system will find out which partition is going to be selected for that particular process, that is going to be decided by this particular placement algorithm. Let's say if your operating system works on a first fit algorithm, then it will find out very first free partition which is big enough to store that process, that is going to be allocated. In best fit, it will find out one of the partition which create very small fragmentation, or let's say allocate the small free partition which is small and enough for the process. That means the difference between partition size and the process size must be very much less, that is going to be selected for the allocation of that process. So here all the partition is going to be searched from top to bottom and allocate that particular partition which is small enough for that particular process to hold it. So obviously it will create a less unused fragment for that particular partition. Now the worst fit is the reverse of best fit. It will find out the largest partition in the memory and it will allocate that particular process into the largest partition. So obviously the amount of space is going to be unutilized, that is going to be more compared to best fit. And in next fit, the strategy, or let's say that is the variant of first fit. In first fit, what the operating system will do, whichever first partition it will find out that is big enough to store that particular process, that is going to be used, allocated to that process. In next fit, it will works accordingly itself, but it will start search where the last one left off. Whenever we have stopped last allocation, from that points onward the searching is going to be started. In first fit, we are going to always start from the top most partition of the main memory. So this particular example we have created over here. So currently this is my primary memory structure, or let's say main memory structure. I have a one partition available of 13 KB, second partition available that is of 11 KB, third partition available that is of 19 KB, fourth partition is available of 14 KB, and the last partition is available of 6 KB. These are the free partitions which are currently available in main memory. Now what we are going, let's say one process comes into the picture of size 12 KB. Now I want to find out one of the partition to allocating this particular process in main memory. So if your operating system works on a based fit, what it will do? It will search for all the free partition and it will find out that particular partition which is small and enough to hold that particular process. So it will start from top of the main memory. So first partition which is free is of 6 KB, which is not sufficient enough to store this particular process. So let's move to the next free partition that is of 14 KB. So if I allocate this particular process in 14 KB, how much memory is going to be unutilized? 2 KB is going to be unutilized. After that, the next process, the next partition is of 19 KB. So if I allocate 12 KB into 19 KB, 7 KB memory is going to be unutilized, and after that next partition is of 11 KB size, which is not big enough to store this particular process, and the last partition is of 13 KB. If I allocate my process in 13 KB, the remaining unused partition is of 1 KB. So after scanning out the whole memory, whichever partition is giving me this less difference between partition size and process size, that is going to be selected for the allocation in best fit algorithm. So according to this difference value, best fit will select 13 KB partition for allocating 12 KB process. Now, if we talk about worst fit, that is the reverse of best fit logic. So it will find out the maximum difference. That means largest memory partition for allocation of the process. So compared to all this 19 KB is the largest memory partition that is going to be selected for the worst fit. Now, if we talk about first fit, so it will operating system will start scanning from the top of the main memory. Whichever first partition is going to be find out for the which is sufficient enough to store that particular process, that is going to be allocated. So obviously 6 KB is not sufficient enough to store 12 KB. So this is going to be ignored. Next partition is of 14 KB, which is sufficient enough to store 12 KB. So that is going to be allocated into the main memory. So these are the different allocation strategy for partition allocation strategy for allocating process to the specific partition. So obviously compared to all of this, based fit are going to be used for betterment. So this is the end of the today's session. In this particular session, we have discussed different what is main memory, what are the main memory management techniques. Then we have focused on contiguous memory allocation. In contiguous memory allocation, we have covered variable scheme and partition fixed partition scheme. After that, we have seen internal fragmentation as well as external fragmentation, and we have seen the partition allocation techniques. That's it for today. We will continue non-contiguous memory allocation scheme in the next session. Thank you.